Hello students, and welcome to section 9-2, adding and subtracting rational expressions. LCM of polynomials. To find the least common multiple of two or more polynomials, factor each expression. The LCM contains each factor the greatest number of times it appears as a factor. Example 1. Find the LCM of 16p squared q cubed r, 40pq to the fourth r squared, and 15p cubed r to the fourth. As you can see, each respective monomial is broken down with its factors, 2 to the fourth, or 2 times itself 4 times. That's fine as well. P squared, q cubed, and r are just written as individual terms, not expanded out as p times p and so on, which you could still do. 2 to the third times 5 is 40. Again, you could also expand 2 to the third. Notice that the other terms are not expanded out. 15p cubed r to the fourth is 3 times 5, but again, the two variable expressions are left as such. They remain as just singular bases raised to those powers. The LCM, in comparing each respective term in factored form, 2 to the fourth, 5, and 3. So I've circled those. Each one of those needs to be a part of the least common multiple. P to the third, and yes, it is true that p to the second and p also exist in the other two terms, but p to the third is the highest of all three. Q to the fourth also is the highest, and r to the fourth also the highest. Please also note, when I did pick 2 to the fourth, 5, and 3, there was a 2 to the third, but between those two, 2 to the fourth was higher. And of course 5 did exist also here, but 5, well, that's the highest it is between all three. And then 3, of course, only exists here. So you pick, as you see, all of those respective terms. When it's all said and done, you in fact multiply 2 to the fourth times 3 times 5, which is 240. Then p cubed, q to the fourth, r to the fourth. That results in your full LCM. Example 2. Find the LCM of 3m squared minus 3m minus 6 and 4m squared plus 12m minus 40. Okay, so the first expression you see is factorable as follows. 3 can be pulled out. As a matter of fact, the side work, as you can see, is factoring the 3, leaving you then with m squared minus m minus 2. M squared minus m minus 2 is factorable as m plus 1 m minus 2. And then of course with this quadratic, a same approach applies where you can factor out a 4, and you're left then with m squared because it divides out of this first term as such. 12m divided by 4 is 3m, and then negative 40 divided by 4 is negative 10. This quadratic is factorable as m minus 2, m plus 5. It turns out 3 and 4 combined give us 12 in the LCM, as you see. M plus 1, m minus 2, and m plus 5. None of the terms that we have in our final answer have a power other than 1. So you just count those in the final answer simply just once. If we happen to have m minus 2 to the second, for example, you'd have to count that in the answer. Okay, moving on. Find the LCM of each set of polynomials. So let's take a look. As you can kind of already see here, we've set ourselves up for what? 14 as the product of 2 times 7. 42 is 2 times 3 times 7. And then 18 is 2 times 3 times 3. So these are the prime factors. When it comes to establishing not just those respective values in the final LCM analysis, but also determining the variable parts of the LCM, A, B, and C, highest exponents of all of them need to be put into the final form. So as we can see, our LCM, yes, it does include 2. That's the highest of all 2's that we see in terms of the exponent, 2 to the first. 3 to the second, okay, even though we have 3 to the first, 3 to the second, of course, is larger. And then 7 to the first, of course, in both of those we only count that once. A squared, there it is, that's the highest of the A bases. B to the second, highest exponent there, and then lastly C cubed. In the end, if we multiply 2 times 3 squared times 7, that's 126. And then you can see of course, a squared b squared c cubed in the final analysis. Let's take a look at number 3. Number 3, as you can kind of already see again, we've broken down 5 times 3, which of course is 65 times 13, which of course is 65. 10, which is 2 times 5, and 26, which is 2 times 13. X to the 4th, y to the 4th appear to be the largest of those two variable base exponent values. So if, as far as the final answer in the LCM goes, you got 2 times 5 times 13. Again, a 2 exists here only once, and again here, but to the first power, and both of those I guess you can say once. You count that in the LCM, 5, and of course also 13, even though you see it in two different terms. In the end, you only have a 13 to the first power, just like 5 to the first and 2 to the first in any given term. That will multiply out as 130 in the final analysis, but of course x to the 4th and y to the 4th, those are the two biggest exponents of those two respective bases. So I'm going to go ahead and scroll down. I do ask that you take a look at number 5 and number 7 on your own. Let's take a look at number 11. So number 11 has a little bit more nuance to it in that you see a quadratic for both first and second terms. So we have to consider, of course, like we saw in the prior example 2 up above, we saw that we can factor and should factor, right? If it's factorable, you should. So the first quadratic you are able to factor as it is a perfect square trinomial. So 3x minus 2 times 3x minus 2. If you FOIL that, in fact, it checks out. 3x squared plus 10x minus 8, on the other hand, is not a perfect square trinomial. However, it is factorable as such. 3x minus 2 times x plus 4. If you FOIL it, you'll see that it checks out as well. So what we see here as far as a least common multiple between the two terms, we have 3x minus 2 technically squared. If you think about it, there's 2 of those in just that first term. And then, of course, x plus 4 exists simply once, but still you need to count that. Highest exponent of which needs to be accounted for in your final analysis. I do want to take a look as we continue down here, maybe at problem 17 and or 18. I actually think 17 is a good kind of following question from what we just discussed and took a look at. So in terms of our first polynomial, in this case a cubic polynomial, you are able to factor by grouping, or at least you should try to factor by grouping. The second polynomial, which is a quadratic, actually is factorable in a different manner. So what I'll go ahead and do is I'm going to start to uncover this as such. And yes, you're going to see number 18, but I encourage you to take a look at 18 on your own later. So take a look. You can factor the first binomial, we can say, arguably separate from the first grouping, such that you have a GCF of x squared and you're left then with x plus 4. Again, that's just this quantity. Similarly, this quantity, if you can see here, changed my third term from a negative into a plus a negative, so that when I do my GCF analysis, it's a negative that I'm factoring, therefore you're left with x plus 4. And if you recall, factoring by grouping, because we get these two to be identical, should yield a factorable situation, of which you can see in the next step, x squared minus 1, and you're left then with x plus 4, which is technically a separate GCF. This quadratic is a factorable quadratic, of which you see x plus 3 and x minus 1. And let's see what we can do from here. Technically, this little binomial is still factorable. And I'll go one extra step with that as follows. X plus 1, x minus 1. So if we're comparing x plus 3 and x minus 1 to this, x plus 1, x minus 1, and x plus 4, the terms altogether, as you can see, you've got an x plus 3, you've got an x minus 1, and you also have one here as well. You've got an x plus 4, and you've got an x plus 1. So in total, you have 4 binomials as part of your final LCM. So take a look. X plus 1, x minus 1, which occurs twice, but still you only counted once, x plus 3, and then x plus 4. I encourage you to take a look at number 18 later on your own, but you'll find in this particular instance it is factorable. And of course there are some nice things that unfold with specifically the LCM, as you can see unfolding as such. Let's finish up on the next page. Now we're going to continue this idea but apply it to a context of which we're going to be adding and subtracting rational expressions. So here we go, add and subtract rational expressions. To add or subtract, you're going to follow these steps. First, step 1, find the least common denominator, or LCD. The LCD is actually synonymous to the LCM, but the math that we'll perform will look very much like when we add and subtract fractions in other situations without variables. And we're going to rewrite each expression with the LCD. Step 2 is to add or subtract the numerators. Because you have a common denominator, you're able to do this. Step 3, combine any like terms in the numerator, which speaks to any algebra problem where you have like terms. You want to combine them. Step 4 is to factor if possible. And then lastly, step 5 is to simplify if possible, which may or may not be applicable. We'll take a look and see how this falls into place here, all 5 steps. Simplify 6 over 2x squared plus 2x minus 12 minus 2 over x squared minus 4. So as you can see, the first step is me taking a look at this first denominator and this second denominator in context of which, if you think about general subtraction of fractions from prior sections and even prior school years, you cannot add or subtract fractions if you do not have a common denominator. So we have to figure, after factoring of course, what common denominator exists. And this is an example of which I actually use to help us understand how and why our LCD will end up being what it is. Let's think about 1/3 minus 1/2. Just for the sake of quick argument, if you were asked to subtract 1/3 minus 1/2, your common denominator would be 6, and the reason is because 3 and 2, as we just discussed on the prior page, multiply like an LCM analysis to be 6. You would have to multiply 1/3 by 2 over 2 to get 6 in the denominator. You'd have to multiply 1/2 times 3 over 3 again to get 6, being again the LCD. I'm calling it an LCD now because it's not just a least common multiple anymore. It's now a denominator that is in fact common between the two. So if you multiply again, this becomes 6, so 2 over 6. Multiply this, of course, this is now 3 over 6. Technically it's 2/6 minus 3/6. Because I have a common denominator, I can officially subtract my numerators, therefore my final answer is negative 1/6. We do know how to find a common denominator on basic fraction problems, adding and subtracting. You now need to understand how it applies with expressions. So for this first quadratic, they factored out a 2. And they also factored it as follows, x plus 3 times x minus 2. Because if you were to FOIL this, you'd have x squared, negative 2x and 3x, which is simply x, and then minus 6. So that's the precursory step to factoring out a 2, and of course you're left with that quadratic. However, it's still factorable as follows. This denominator is also factorable as follows, x plus 2, x minus 2. So what happens is you have to look at these two factored forms with respect to an LCM, but now technically an LCD as we're framing it, where you have 2, there it is, x plus 3, x minus 2 twice, but we're only going to count it once, and then lastly x plus 2. So we're going to multiply this first fraction by x plus 2 over x plus 2. I highlighted it in green. And that's all you need because technically it has everything in its denominator except x plus 2. Similarly, we'll multiply the second fraction, but instead of just one thing, it'll be x plus 3 over x plus 3, but also 2 over 2. Once you do this, once you establish the LCD, you can start to manipulate the numerators. I'm going to multiply 6 times the quantity x plus 2, and negative 2 times 2, the quantity x plus 3, which yields this, negative 4 parentheses x plus 3, distribute. And the next step, you're left with 6x plus 12 minus 4x minus 12. Nicely, the 12s cancel. The denominator is still that whole quantity as we see. Simply 6x minus 4x is 2x. Then the next step, the 2's nicely cancel. And what you're left then with is x over the quantity x plus 3, x minus 2, x plus 2. This is the final version we need to denote as our final answer. If there's any common factors, we'll divide them out, and any precursory or follow-up steps to this. And any precursory steps, you'll see hopefully other factors cancel. We'll continue this when we're together. Please take a look at some completed examples.